Hi, we are alive.
Hi, everyone. Welcome to the RSK Community Call for this month. Welcome, everybody. I see a lot of familiar names in the chat. So glad to see all of you here. Talk to all of you in open Slack and all of those other things. And, great to see the family growing. So I'm Brendan. And today we'll be hearing from many members of the community, including yourselves. So this community call is all about RSK IPs. So how do we make RSK better? So the link for that is on GitHub, right? And it works in a very similar way to EIPs. It's open source and it's all there. We'll go into that in a little bit more detail later on. And here's the agenda for today, right? So the first 10 minutes, we'll be doing an introduction to community calls. The next 10 minutes, we'll be talking about the RSK IPs, about RSK IPs. That's interesting, just to set the scene. And then another 15 minutes, we'll be talking about RSK IPs related to gas costs and transaction fees. And then another 15 minutes, we'll be talking about another 2 RSK IPs to do with fork detection. And then we'll round it all up with questions and answers. So let's start the conversation. So I know a lot of you are tuning into this using some live streams, and you can ask in your questions and your comments in the comments there. But we'd also like to bring you into a part of a more ongoing conversation that will not end as soon as this this live stream is over. So we'd invite you to join a couple of places. First is our open Slack. You can click on this link. Someone will paste it in the chat for you, developers.rsk.co/Slack. And when you go there, it'll basically give you an invite to something that looks like this, right? Join the research and innovation channel, and you can ask your questions there live during this call as well if you want, and we'll get to that towards the end. The other thing you can do is you can join our discourse forum. So this is where our RSK IPs, they get discussed as well in more detail. So you can use that to propose your own as well as discuss existing ones. So we encourage you to join research.rsk.dev. All right. So we would like to introduce you to the community calls, and I believe that Adrian, you'd like to say some things about it.
Yeah, thanks, Brendan. Hi, everyone. So the idea behind these community calls is to find ways to get people involved in the evolution of the RSK platform and to gather feedback from the different RSK stakeholders. The RSK platform consists of several technologies, including the protocol itself, the RSK protocol, but also the RSK client implementation, that there is only one now, that is RSKJ. Hopefully this will change in the near future. The layer 2 applications and services, the bridges, etc. This space, as Brendan was saying, and as we envision it now, will be focused on the core protocol, basically the rules by which the blocks are added to the RSK blockchain. Right? So historically speaking, this has been led by a small group, mostly from IOB, except for the consensus rules that are set on chain, for example, the block gas limit or the transactions minimum gas price that are defined by the miners. But in general, these are the teams and the small group that has been leading these efforts. But it's necessary for the ecosystem to evolve, that more people and more shareholders get involved, not only the teams working on the client implementation, but also the teams working on solutions on top of RSK, mining pools, the RSK users, etc., and that they have a say in how the platform will evolve. You probably know that there is a network upgrade happening soon that is called Iris, but with this meeting today, which is the first RSK community call, we want to formally kick off the discussions for the following RSK network upgrade. It's called HOP, at least for now. So we will have people from the IOB research team first explaining the process by which changes to the RSK protocol are proposed and discussed and selected, and then they will be presenting a few improvement proposals they have been working on as candidates to be part of HOP. And I understand there will be some time for QAs at the end of the presentations also. One important thing is this meeting today is not a decision-making meeting. There are no decisions around the protocol and the network upgrade being made today. These discussions will continue on different communication channels Brendan mentioned before, and the following community calls. And well, finally, this meeting will happen around every 4 weeks, although it's not like yet defined, but more or less that will be the frequency, at least at the beginning. And I understand, Brendan, that this meeting is recorded, so yeah, make sure you feel comfortable with that, right? And well, that's basically it, a very brief presentation of what we expect from this space.
Awesome. Yeah, and just to underscore that very first point, we really want to get the community more involved in the process of RSK IPs, and that's the big thing for us here. That's the big purpose. Okay, thank you very much. So the next topic we have is RSK IP 0, and we're keen to hear from Sergio. So do you have some slides for this? Do you want to take over the screen?
Mm-hmm. Yes. Thank you, Brendan. Share screen. One moment. Okay. Let's share screen. Okay, do you see the screen?
Yep.
Okay, perfect. Okay, I lost the audio return. I hope you are still there. So the RSK improvement proposals are documents that you submit to the community so that you can propose changes for the consensus protocol. Oh, it's kind of hard without the audio feedback, but I suppose you are still there, but it's kind of strange. Okay, so this is the repository where you can find the RSK IPs and you can propose new. The process of writing and evaluating and merging RSK IPs started in 2016. There have been approximately 30 people involved in the writing and evaluating RSK IPs. So even if it was a small group, it's not a very small group. It has people that are now in IOB labs, but also people that are from other companies collaborated. There were 244 proposals, and that's really a lot comparing to other networks. So there was a lot of activity. Although some of them have been abandoned or are still incomplete, and the champions, the authors, are still need still to review. From those 244 proposals, 137 proposals have been merged. This means that they have been analyzed by the editors of the repository, and they find the descriptions are clear enough for the community to evaluate. And from those numbers of proposals, about 40 of them have been adopted by the RSK platform and activated in the different network upgrades. Okay, are still you there with me?
Yes, we are.
Yes.
Thank you. It's very hard without a return. Okay, yeah. So these are the RSK IP editors. and Diego Macinis, me, Julian Len, Shreemoy Mishra, Javier Alvarez Cifuentes, and Raul Laprida. And these are the people that are behind this repository reviewing. We split the task between among us so that it's not too much load. And essentially, nobody can review his own proposal. So if I submit a proposal, then some other reviewers must review it. The process to submit a proposal starts with a draft, which is a document where you sketch your idea, and the most detail you put on your idea, then the easiest for the community to analyze it. So if it is very superficial, then probably the RSK IP reviewers will ask you to put more detail. Okay, so you can start with a superficial proposal, but as this proposal evolves, we will also ask you to fill in the gaps and complete, because unfinished proposals are very hard for the community to analyze in depth. Okay, so the proposal starts with a draft, and then it can be rejected because the community finds it's no value to the platform, or it contradicts some fundamental genesis, concepts of the platform. For instance, if you would like to change RSK from proof of work to proof of stake, then I don't know, probably that would be rejected because it's not in the in the white paper of this platform. But generally, if it's good, it will be moved to be. If the community finds it is useful for the platform, and this is discussed generally in the research forum, then it will be accepted, which means that it will be pending for the following network upgrade to be activated and adopted, right? So if it is a change in consensus, we say it is activated. If it is any other change that does not involve consensus, for instance, it is a change in the interface with the node, or it is a change in the command line arguments or in the network packets, then we said it is adopted because it's not really activated. Okay, so basically this is the workflow of a proposal. So what does a proposal need? First, it needs a preamble where you fill some metadata about the RSK IP. For instance, the name of the person who has written it and who will push it through all this process, and also some links that I will show to where the community can discuss it. Then you have to fill a short description, an abstract, and this has to be as short as possible, so that you can very easily find if it is interesting, if it is important, all related to the proposal. And then you write the motivation. The motivation are what problems this proposal solve. Okay, essentially there are several kinds of consensus changes on the platform. They can be related to the security of the platform. They can be related to the fairness, to the scalability, okay, to the usability of the platform. These are different categories of proposals, but essentially each proposal has a strong motivation. So if we put a lot of effort, because network upgrades requires a lot of effort from all the community, node maintainers, industry, miners. So it's very important that the motivation it's strong. And then you write a specification of this proposal, and the specification must leave out any opinion, any that should be in some other parts of the document. This is just what is the shortest possible way that you can express in a formal way or in a precise way what are the changes needed for the platform. The next section is a rationale where you will write the design decisions behind this technical implementation. Generally, the problems have many different solutions, and you are choosing one. So you have to justify or argue in favor of this particular solution. So it's good that you also show what are the other solutions that you have discarded, or that what are the other related RSK IPs that you have evaluated, and why you have discarded, and why this is better than rest. If you have statistical data or tests that you have performed, let's say performance test or verifications or everything that it's useful for the community to evaluate and justify this proposal goes there. And then you specify if there's any backward compatibility problem and how you are addressing this. Of course, we will strongly prefer things that do not break compatible. Essentially, we do an enormous effort to keep immutability of smart contracts, and so anything that can break this property obviously will be very criticized by the community. And then you can optionally write an implementation, and also you can provide the test cases. So at this point, because we want really to encourage the community to participate, you can submit your RSKIP, and you can leave out the implementation, and maybe you can put just a few test cases that you made by hand. But as we progress, we will try to ask the proposers to provide the implementation and the test cases. Okay. And finally, we have a copyright waiver. So everything you publish here is public domain. And we will try from the editors that try to help you make this proposal clear. But the technical discussion about the proposal has to be in a forum. We propose that this is the RSK Research Forum. Okay. But here we will only discuss, if we interact with you, what you can make to make this document better for anyone to understand. Okay, that's the role of the RSKP editors. So this is the preamble header. So you have a number, the title, the date of creation, the author, which we generally put initials, and then we fill the name in some other places in the index. Then we have the purpose, which can be security, fairness, privacy, scalability, and there are several of them. And the layer that it involves, the complexity, we have so that the implementers can know if this is going to be hard and assign resources to this, if this is going to be implemented by a third party. The status that I talked before, and where the technical discussions are happening. Okay, and generally to fill these numbers, and what we generally do is we create a pull request with a RSKIP with any number, let's say XXX. When you create a pull request, you are assigned a number by GitHub, and that is the number of the RSKIP. Okay, so you create a pull request, you get a number, you go back to your local repository, you rename the files, and then you push back the changes. So that's how you get assigned a number. Okay. Okay, so that's all. All this information is it's part of the RSKIP 0. So I encourage you to read it, and you can have all clarifications about what I've just explained in this document. Okay, thanks, Brendan.
Awesome. Thank you so much for that. So let's move on to the next topic, which is RSKIP 239 and 240. Both of them are about changes to gas costs and transaction fees. I believe Shreemoy, you're up, right? Do you have the slide deck?
I do.
Okay, let's share that.
Okay, thanks.
Awesome.
Okay, so Sergio already mentioned the audio might be a concern. Let's see how much it bothers me. But yeah, thank you very much for the opportunity to come here and talk about two RSKIPs that I've been involved with. This is jointly with Sergio and Diego Massini, and they're both related to some proposed changes in the structure of gas costs for processing transactions. Oops. So big picture changes about both of them together. They both are targeting changes to the cost for accessing blockchain state. And the objective is to align transaction fees with the resources transactions are actually using at the level of the nodes. And so they target improvements to performance, to scalability, to sustainability, security, and these will become evident as you see some of the details. The approaches are twofold. It's a combination of changes to some existing fixed costs, and the second RSKIP introduces new variable costs, which we are calling storage rent. So it's helpful just to think about example. A token transfer is often the canonical case now, so just think about that. A token transfer from a user to another involves the transaction touching several parts of the blockchain state. This includes the sender's balance, because the gas comes from the sender's balance, so we must touch that account. The transaction must read the contract code that's deployed in the chain, and then depending on the transfer, it has to change the values in the contract store itself from the sender's map to the receivers. So these are an example of a transaction touching many parts of the state trie. Currently, the fixed cost of accessing these pieces of data from the blockchain are 400 to get the account information. It's 700 to load contract code. The call is just one example. There are other codes that do this. External code copy, external code size are two other examples. And to read storage cells, we have an opcode sload that costs 200 gas. And for context, the overall base fee for a transaction is 21,000. So these are added in addition to the base cost. Some recent experiments show that the actual performance cost at the node level for reading information from the tree can be kind of on the higher side than these costs would suggest. For example, on average, it costs about 30,000 nanoseconds in terms of resources used to read a single node. And using a factor of conversion between execution time and gas of say 1 to 30, and the RSKIP has details on how we come up with these numbers, if an action takes 30,000 nanoseconds on the VM, then we should be charging 1,000 gas for it using that ratio 1 to 30. But an S-load just costs 200. As you'll see in the RSKIP, there's more details on the actual time depends on how much of the state we have cached on the computer's RAM. The more we cache, the faster these reads get. So there's a trade-off there. But the general idea is we believe these reads are quite underpriced. And so this first proposal tries to correct for these pricing errors by raising the price of two very frequently used opcodes, the balance and the S-load for reading storage cells. So as you can see, these costs are being revised from 400 or proposed to be revised to 700 for balance. A very tightly connected operation is the external code hash, costs about the same in terms of resources. So the proposal calls for also increasing that from 400 to 700. No changes to call, but the reading cost of the storage cell, which we think is the most underpriced, is proposed to be raised from 200 to 800. We could be more aggressive, but since we're not really sure about community's feedback, we're going with a conservative change right now. Suggestions are kind of on the conservative side, and they are pretty much in line with the gas structure in Ethereum when they adopted Istanbul in December 2019. Now, moving on quickly to the second proposal, this is more of a qualitative change. The first one was more of a quantitative change. This is the idea of introducing storage costs with a time dimension. Right now, all storage costs are just based on changes made to a storage cell, which is about 32 bytes max. But it doesn't matter if you store something for 1 year or 1 day, the cost is about the same. And storage rent tries to change that. Again, let's just think about the same example of a token transfer. It touches all these different parts of the state trie, and we want to introduce a fee version for these access costs that's duration based. How long has the information been stored on the chain? but it may seem like we are paying rent for just time. But to clarify, this is still about disk I/O. As you'll see, the idea is that if there is a contract that no one has used in 2 years or 3 years, then the chances are it is not in RAM, and it's going to cost resources to bring that contract to RAM and to process the transaction. So nodes that have not been touched in a long time will have more rent due. Nodes that are used very frequently will have their rent updated. And this is indicated by a timestamp. And so the basic idea is this can serve in the future as a caching hierarchy. We can use the rent status to say, these nodes are frequently used, let's keep them in RAM, and these nodes have not been touched in a long time, they can stay on disk. So we can prioritize which ones to keep on RAM. These are some of the desired or hope objectives of why we think this is a good idea. It just makes basic sense and good economics to have a time dimension to storage. Just like AWS does, you pay for gigabytes of storage and also per month. IPFS and the other blockchain storage services also have a time component. Rent introduces a cache hierarchy. Just like some related changes in Ethereum, specifically EIPs 150 and 2929, which raised gas costs as a way to mitigate the risk of DOS attacks, storage rent can also serve as a DOS mitigation strategy. And it reduces the risk of storage spam and gas arbitrage, which is people trying to occupy, it's like a land grab on the blockchain storage space. To prevent such things from happening, a storage rent can assist. A little bit more on the specs. The proposal calls for adding a Unix seconds timestamp to every try node, so we can keep track of when was rent paid for that node last time. And the rent for a single node would depend on how much data it stores. For example, the storage cell can at most store 32 bytes. So it depends on the time that rent is collected for, the node size, and we also propose some triggers and caps. The details are in the RSKIP, but the idea is we don't want to collect one gas in rent. We want to avoid collecting small amounts. And also making changes to the timestamp implies a new try operation. And it's resource intensive to make changes to the try just to update the rent. So there are triggers, minimum amounts that must be met to collect rent in a transaction. And there are overall caps so that the costs are spread across transaction. No single user ends up paying a huge amount in a single transaction. To make these more concrete, here are some examples. The specification calls for an approximate rent of 15 gas per byte. So that's kind of on the low side and infrequent. Because it's a new mechanism, it's a qualitative change, we want to be careful and cautious here and get feedback from the community. Typical examples of an account, the rent may be around 2,100 gas a year. So you can see it's 10% of a normal transaction, not very high. For a storage cell, it's about 2,400 gas based on 32 bytes maximum. And for contract code, of course, it depends. It can vary on the size of the code. This example is for 4,000 kilobytes. For reference, the sovereign transaction token transit contract is about 3,900 bytes. A simple ERC20 contract is 2,400 bytes. And the RIF token is around 16 kilobytes. So the rent for the code depends on how large your code is. But to get an idea of frequencies, we have set some triggers so that accounts don't have to pay rent more than once or twice a year. So most transactions, rent will be rarely seen. For most users, they won't even feel that there is any rent. The storage cell is about the same, once or twice a year. Contract code, for if it's 60,000, then maybe 2 users or 2 transactions per year would end up sharing some of this rent for the contract. And again, it's based on details of triggers. What's the minimum amount collected? What's the max we can collect? So as Sergio mentioned, any kind of changes, the first priority is to reach out to the community and check for any compatibility issues, breaking changes. So that's sort of one of the first things we are looking for. I have been looking at replaying transactions to see which ones break. I haven't found any so far that break without just sending more gas. Simply sending a bit more gas makes things go through. But that's one of the things we hope the community will reach out and tell us about the concerns. Similarly, there are other details that I can't go into today about how do we stop having side effects where there is a call revert. Do we change the rent timestamps? We don't want to if no state changes are occurring, but we don't want to keep all the rent collected either. So there are issues like that, details in the RSKIP. Please take a look at it and let us know on the forum or GitHub issues, whichever channel you prefer, what your concerns are, so we can move forward with this proposal. Thank you very much. I think I'll just stop there and see if there are any questions.
Awesome. Okay, so lots of questions, but I think we'll save most of them till the end. But I just want to point out this one question from John. Who will pay storage rent for contracts that have many users, such as token contracts or DEXs?
So the proposal just says we keep track of outstanding rent, and there are triggers. So if I am the user who is sending a contract at which point the outstanding rent is, say, 15,000, then that 15,000 is put on my gas for that transaction. So it's random users. So if a contract has 1,000 users regular in a year, 2 out of those 1,000 will share the cost for the transaction. So it's sort of randomized, and it's capped on how much an individual user can pay. It's possible that I am the user who ends up paying twice in the same year, but that's going to be really rare.
May I add something? One of the differences between this proposal and some other proposals is this: the rent is collected per tri-node basis. This means that if there is ERC20 token, you are not going to pay the rent for all the balances, just for the 2 balances that you are touching, right? Not all. I mean, if it has 1,000,000 balances, you are not going to pay rent for all that. Just for the balance that you touch, the source and the destination balance. The part that is shared, yes, is the code, right? That is the part that is shared between several users.
Yes, that's the idea, but we hope these will be infrequent enough that most users will not be impacted. And yes, you only pay for the nodes that you touch, your transaction touches. So a token transfer, or the nodes touched are your own account balance, the code, and the 2 storage cells, not for all the other hundreds of users. Are we keeping more questions for the end? Move on.
Yeah, we'll have more questions at the end. For now, let's move on to next 2 RSKIPs. So I believe, Sergio, it's you're up again. RSKIP 223 and 224 about fork detection. You're on mute, Sergio. And thank you very much for the great question, John.
Okay.
All right.
Do you see the screen?
Not yet, no. Okay, now we do.
Oh, okay.
Awesome.
Okay, so the RSK IPs I'm presenting, this 223, 224, are related to the security of the RSK platform. And as you know, I've been working trying to secure this platform from the beginning, and for me, it's the main priority. It has always been. So if we take a look at the hash rate since the genesis, it has been going up constantly, almost always up, with certain ups and downs, but essentially we are going up. We reached at some point 70% of the Bitcoin hash rate, and we are on average in the 65% of Bitcoin hash rate, and that's a lot, and that puts RSK in one of the most secure blockchains thermodynamically, right? But still, we should never rest on our laurels. We should be vigilant, and we should stay vigilant to make sure that under no circumstances the platform becomes insecure. Okay, so Why are 51% attacks important? Because there have been 51% attacks on a lot of blockchains from 2012 to nowadays. So we want RSK to be strong, to have several layers of security protecting from 51% attacks. So in the past, we created in a previous network upgrade, we created a system that is called Armadillo that protects RSK from these from attacks by providing the community with distributed alerts that can be used by full nodes to sense what is happening with the network if there is a kind of attack ongoing. It never happened from the genesis until today, but we used the Armadillo system, and it worked fairly well to detect malfunctions of miners, for instance. Okay, so there are two types of kind of 51% attacks. The one that they call revert after confirmation, where a user sends money to an exchange that is confirmed by the exchange. The user takes out the fund, and then the malicious user tries to revert the RSK blockchain. And that is very expensive, because since you have there's a lot of time gap there, you have to catch up with the on exchange, and that's generally, we consider this almost impossible. But yet we added in the Iris hard fork a protection against this attack, which links the timestamps of the RSK blocks and Bitcoin blocks, so that if you want to perform this attack, you have to waste all Bitcoin rewards, because those will not be valid Bitcoin blocks, right? And the other one is called revert during confirmation, where the attacker in parallel tries to build a private malicious fork of the blockchain, okay, to at certain point surpass the on exchange after the transaction has been confirmed. And this is the scenario that Armadillo protects RSK. But so what Armadillo does? Armadillo looks this malicious fork. It can detect this by looking at the Bitcoin blocks, the RSK tags in the Bitcoin blocks, and build a graph of what's happening, and can distribute alerts to node operators saying, okay, this is happening. Here's the proof. These blocks are creating a malicious reorganization of the blockchain, and so nodes can stop accepting confirmations. Of course, this has never happened, as I told you before, but we are prepared for this scenario. But still, we can do better, and I think that our responsibility as the RSK community is to do everything possible to avoid any kinds of attacks. Okay, so this is how the merge mining looks. We have an honest exchange, which is the RSK blockchain in the bottom. We have the Bitcoin blockchain in the middle, and these are connected by some of the Bitcoin blocks are connected to RSK blocks using these RSK block tags. And if there is an attack ongoing, some of these blocks will connect to tags that we cannot identify. This is previously Armadillo was deployed. We had this state. We could have this state where we know there is something happening. We know that there are some Bitcoin blocks pointing to an unknown, a private, a selfish, maybe RSK chain, but we could not connect these blocks. What Armadillo did in RSKIP 110 is to be able to distinguish between two scenarios. One, which is the attack scenario, where we have a fork that is connecting blocks one to the next, so it's building a parallel chain, and the other, which represents simply a malfunction of the mining network of a certain miner, which is a miner mining uncles of the blocks in the main chain. Okay, so before RSKIP 110, we could not distinguish these scenarios, but now we can. Okay, but we want to do better. And how Armadillo works, it adds to the RSK block tag some pointers to previous checkpoints in the RSK chain. Okay, so basically we can use these checkpoints to find a checkpoint overlap between different blocks, and that allows us to connect those blocks with high probability. In this example, the block, the dishonest RSK block 130 in the upper chain, it's pointing to the block 128, the block 64, and the block 0. And then the following block, the attacker's block 200, is pointing to 192, 128, and 64. So because there is an overlap in checkpoints, we can, with high probability, join this and build a chain. Okay. And what I've said at this point is just how RSK works right now. Okay, this is working for, I think, at least 2 years or a year now. Okay, so what do we need to know about a fork to be able to take informed decisions and to be able to give the community precise data to act? We have to know what would be the damage of this malicious fork, and we have to know what is the probability of success of this fork. Okay, so the damage we measure saying, when did it start? How many blocks will it revert if the attack is successful? Okay, and the probability of success is given by the fork hash rate. So how much hash rate is backing up this malicious fork? How quickly it is growing? Or what is the risk that it overtakes the honest chain in the following hour? Okay, so when we can connect the attacker's block, all this information is provided to us. Okay, so the key thing that we have to do is connect the attacker's blocks. How this is done with Armadillo, RSKIP 110. Okay, so the original RSK block ID was split into several fields. One is still the RSK block ID, but now it's shorter, it's 20 bytes. And we added a field called commit to parents vector, which has these checkpoints to the previous blocks that we use to find the overlap. Okay, then we have a field that specifies the number of uncles in the last 32 blocks, and then we have the block number. All these fields are very important to be able to reconstruct this graph. But here's how do we match the different commit to parents vectors. So in this example, we have 6 different blocks, and some of them match in fully with the previous one, and some of them match in leaving out a couple of slots because maybe there was a period of time where the attacker could not mine a Bitcoin block. So, but essentially we can always overlap them, okay, and find that they are connected. But what we already knew when we developed this proposal is that if the attacker decides to mine uncles instead of mining blocks from the main chain, then it can try to hide the fact that he's mining. So we will be able to detect that there is a lot of uncle blocks, and this would be suspicious, but we would not be able to connect them. Why? Because we are creating these pointers that jump 64 blocks of the main chain. So in this example, the attacker has created only 19 blocks in the main chain, but since each block has 10 uncles, 10 sibling blocks that contribute to the hash rate of that fork, then the actual hash rate of this fork is not equivalent to 19 blocks, but to 190 blocks. Okay, so we want to be able to track this scenario with precision. And so what RSKIP 224 proposed is a very limited change that does not affect anything else of the platform except this security system, which is basically changing the field commit to parents to commit to, I call it, family members. So instead of these checkpoints going back 64 blocks, it goes back 64 family members, which can be main chain blocks, but it can also be uncles. Okay, so basically with this change, we we in the RSK block tag now we have pointers that can point to uncle blocks. So this is how it will look if we analyze this attempt to attack RSK. We will see several checkpoints pointing to the attacker's blocks, so we will still be able to connect them. Okay. What happens internally is that the blocks are linearized, so and then we just create pointers taking each one of 64 of these linearized family member blocks. Okay. Another thing that we knew and we want to improve now is that what happens if the attacker tries to increase the block difficulty by tweaking the timestamps, so that to keep less number, to create a fork that has more hash rate in less number of blocks, so that he can hide his checkpoint. So he can still have a single checkpoint that points to the honest chain. So we won't be able to connect the attacker's block. Okay. So for doing this, the attacker has to play with the timestamps, put them shorter timestamps, and put more mine with a higher difficulty. We can we can also detect this attack, but we won't be able to chain blocks. And so what we propose in RSKIP 223 is to add to the merge mining tag a small field, a compressed field of 64 bits that expresses the cumulative difficulty of the fork up to that point. So we won't be able to directly connect the blocks, but we will be able to detect very easily that the attacker is trying to increase the difficulty of the blockchain to be hidden from the detection. So with this change, it would be very, very obvious that it's an attack. Okay. So the only, I would say, drawback of this proposal is that we have to extend the tag, and this involves making sure that the softwares that miners are using to merge mine allows the tag to be longer than 32 bytes. And in the RSKIP, we propose for a time to let the miners use both formats until we make sure that they are ready to use the new format. And once they are, we can deprecate the old tag format. So there will be a time where both tag formats are active, and that's why we added to a tag a version number, which is this field that was inserted here. It's a ver vn4, which contains 4 bits for the version number and 4 bits for the block number. So it's a split byte there. So yeah, I think that I explained everything. Please read the RSKIP. I've been very, very light in the explanation, and I invite you to discuss this in the research forum. Thanks, everyone.
Okay, amazing. And I see a lot of comments in going on the live stream. So lots of questions, and it's time to do that now. So let's do this. So right. So the first question was a bit of a fun one. How do you pronounce RSK? Well, I've just pronounced it the way I do. I never really thought about it. Does anyone pronounce it differently? No?
RSK.
Anyone can pronounce it as they want. No, some people call it Rostock, as was the original name, or RSK is fine. RSK in Spanish.
We've called our community Rostockers. So you can call, if you feel you are a Rostocker, you just can call it Rostock.
Awesome. Okay. Then there's another question about Taproot. Will Taproot help RSK be more efficient and capable?
Yes. This question is not related to what I've said, but Taproot brings several improvements. So one of them is to create scripts, multi-signature scripts that are that can contain a lot more pegnatories, a lot more signers. So this is something that could be used by RSK to expand the POPEG, for instance. But also Taproot is the basis for new changes that will come later. Okay. Another interesting thing of Taproot is the activation of short signatures, which has very interesting properties related to threshold signatures. So that's another way that we could improve the POPEG by creating a threshold signature which occupies less space, so payout transaction will be cheaper. Of course, we have to wait until Taproot activates, and then we have to make the proposal for RSK and then activate them. So it will take time, but yes, it's important for RSK.
Awesome. The next one is a bit of an easy one. Is RSK built on the Bitcoin network? That's a true or false. The answer is true. In case you didn't notice, like Sergio was going into all of the details about how the blocks within the RSK network, but you could see the arrows pointing to Bitcoin blocks. So there's your proof. But does anyone want to add anything to that?
I like to think, yeah, go ahead. Yeah, go.
No, I was just going to mention that RSK was actually the first production Bitcoin sidechain ever launched in production. So completely linked to the Bitcoin network on the merge mining side, as Sergio was explaining, and also using Bitcoin as native currency, which makes the sidechain part of it.
Mm-hmm. Yeah.
I think
sidechain and also first Bitcoin smart contract platform, and I believe the only one still.
I like a sovereign characterization of rootstockers as Bitcoin mutants. Like, we are Bitcoiners, but we feel that there is a lot of interesting technology that's being developed outside the core Bitcoin protocol that should be connected to Bitcoin. So the best way that we can provide value to the Bitcoin network and use these new technologies is by creating a Bitcoin sidechain. So RSK is the first Bitcoin sidechain. Is very Bitcoin centric in that regard.
Awesome. Okay, and then there was also a question about where to find information about the Federation Bridge, right? And we've already replied to you in the comments. But the specific question was, how many nodes are there and who is controlling the multisigs, or who are controlling the multisigs?
Adrian, do you want to, I don't know if he's on stage?
No, he's not.
Okay.
Sergio, that would be you.
Yeah, okay, so I'm not have the names. You can find them in the RSK webpage. I think there are about 12 pegnatories. These are independent companies in the community. Each one of them holds a hardware security model that protects a private key. They are so I don't remember what are the first part of the question, but that is regarding the POPEG, right? What was the first part?
So how many nodes and who's controlling the multisigs?
I have no idea how many nodes. I know that there are hundreds of them, but I don't have personally. I don't track who's running the nodes.
And Sergio, maybe you can explain, because the way the question is framed on how controls the multisig, that actually the POPEG members do not control the multisig. It's just they're running the hardware security models, which are tamper-proof, and they can actually not send or choose which transactions go the POPEG. Maybe you want to clarify that.
Yeah, you've said it very clearly. The pegnatories, each one of them has a hardware security module running a secure element inside that protects the private key, and will only obey the honest chain by checking the proof of work. Okay, so even in the case of 100% collusion between POPEG members, between pegnatories, they won't be able to to arbitrarily transfer bitcoins out of the platform. So it's I think that it's an evolution of a federation, a very, very stronger, much stronger security system than a typical multi-sig federation.
Yeah, maybe Adrian, would you like to add on to that?
Yeah, I think you have already shared links, but yeah, in rsk.co/POPEG, there is a list of current members of the POPEG that we call the pegnatories. These are the ones running the HSMs, as Gabriel and Sergio has just explained.
Okay, awesome. Right, and I guess the final question was actually more of a discussion about using Thor chain for moving between BTC and RBTC. Is that within scope for today's thing? Because we can wrap up otherwise.
Using what? Sorry.
Thor chain, THOR chain.
Oh, yeah. I think that's out of.
Yeah,
topic.
I thought so. Okay, but
feel
free
actually,
to.
sorry, yeah. Brendan, there was an answer from John Light.
Yes.
I think it was quite accurate in terms of it's not the same like swapping tokens than like doing the going through the POPEG process and doing peg-ins and peg-outs. So I think that was a good answer for that.
Okay, awesome. Okay, so I'm gonna try to get my screen back on. Bear with me 1 second, and we'll wrap up. So
I have a question for Adrian and Sergio. Is there any timing that we expect the community to provide feedback? When do we think that these RSKIPs could be merged or discussed publicly? I mean, what's the timing on this to give a reference to the rest of the community?
Yeah, so I think that at least my understanding, maybe Sergio can complement that, but we are like still in a very early stage because we are like currently wrapping up the Iris network upgrade. So it's hard to say, and I would say that defining that it's also part of the discussions we want to have. My personal opinion, and but not sure if the rest share this, is that that, for example, in the case of Iris, is a big network upgrade. So it took several months. We've been working on that for a long time. I personally think that having like shorter time frames and having a network upgrade in a shorter period of time, maybe in something around 3 months, once Iris is activated, is something that could make sense. But that's again my personal view on that.
Yeah. Well, in the past, what we've done is that we've all the community members have discussed what are the features that we wanted to have in the platform. We discussed them. We took feedback, and then we didn't put a date to the fork, but we just waited until the programmers and collaborators were ready with a high confidence that everything was ready from the code. We can do differently. We can propose a certain date and then remove features as we approach those dates if those features are not ready. But I think that's the current workflow where we base our dates on features and not the other way, has been very fruitful.
Awesome, thanks.
Awesome. Okay, so we're at the end of today's community call. Thank you so much, everyone who joined us and for sticking through till the end. But we'd like to continue the conversation, if not in this live video format, but also in chat on our open Slack. So please join at the link developers.rsk.co/Slack and join the research and innovation channel, and ask all of the amazing questions that you've been asking in this chat. Continue asking them in Slack. Also, to propose and discuss RSK IPs, research.rskdev is where you want to be. That's where the RSK IP specific discussion is focused on. And within that, we also have a post that the link is on the screen as well for the next community call. We're aiming for somewhere in June or July. And so we want to hear from you, right? What do you want to see in our next community call? What do you want to be discussed? Feel free to make proposals. You can propose your own RSK IP, or you can vote up an existing RSK IP, and we'll try to talk about what's most popular, or what's most pressing for all of you. All right, and that's it. Thank you very much for everyone for joining. Ciao. Good morning. Good afternoon.
Thanks, Brendan, for the organization. Thank you.
You're welcome.
Awesome, Brendan. Thanks.
Bye, guys.
Bye, everyone.
Bye.